So my name is Subin Govind. I work for Dell Technologies out of Santa Clara as a senior principal engineer. And today I'll be talking about implementing HDFS ACLs in OneFS. So before we start, a few terms that I want to lay down, right? OneFS is the operating system that runs on Dell PowerScale systems. PowerScale is formerly known as Isilon. I got the multiple questions this week, like, what is PowerScale, right? So PowerScale is actually Isilon, if you guys are familiar with that. HDFS is an implementation of POSIX ACLs, and OneFS ACLs is essentially a superset of NTFS ACLs. So the point here in this slide is that I'll be using HDFS ACLs and POSIX ACLs interchangeably, as I would be doing for OneFS ACLs and NTFS ACLs. So they're basically the same thing. It's when there is some specific, something specific to OneFS ACLs, I'll make that explicit. Okay, so we'll start off with mode bits, right, and the permission checking algorithm associated with it. Then we'll talk about OneFS ACLs and the permission checking algorithm. Later we'll talk about POSIX ACLs and again the permission checking algorithm associated with it. Then we'll proceed to the design approaches that were available to us at that point and what we chose. In the end, we'll look at concurrency and replication issues related to the HDFS ACL implementation on OneFS. Okay, let's start with permissions. So OneFS supports three kinds of permissions. It supports POSIX mod bits, NTFS ACLs, and NTFS ACLs, right? And on top of that, we have what is known as ACL policies. These are basically config knobs, which allow customers to tweak the behavior of access control. So why do we need this? We need this because there are certain multi-protocol scenarios where you don't know what the behavior is. Like a very good example of this, which I give people, is what if you want to do chmod on a NTFS ACL? The behavior is not defined. So what we have in OneFS is we have many implementations of chmod, right? And I have seen a lot of people coming forward and saying that, no, this is the right implementation of chmod. My implementation is the right implementation. But it's all, each person has its own idea of what is the right implementation. So ACL policy lets us choose among the implementations that we have. Okay, let's talk about basic mode bits, right? Mode bits is, like everyone knows mode bits. Mode bit has 9 bits. The thing to note about mode bits is that the evaluation algorithm follows first match semantics, and I'll define what first match semantics is a little later. You start off by, the permission checking algorithm first checks whether you're the file owner, then it checks whether you're in the file group, and then it goes with other sets of bits. And this is important to understand. There are certain points in mode bits permission checking which are not really clear when you first look at it. And it's needed to understand POSIX ACLs. So this is a basic, anatomy of a permission checking call, right? So it has 3 components. You have, on the left, you have the permission of the file. On the right, you have the creds and the requested perms. So the creds are essentially the identity of the user. If you look at it, in this case, it's the user Alice, who's a member of engineering. And the requested permissions are what Alice wants on this file on the left. So this file has RWX, RW, and R-X. So, so this is what a permission checking algorithm, or if you want to represent it, this is what it will look like. The thing to note here is that the permission checking bits are, the bits actually represented here in what do you call them, ASCII notation, right? And this example, I'll be adding to this example in subsequent slides, and I will be extending it to make, so that we have a common reference for permission checking algorithms. So this is the happy case, the easy case where Alice actually wants to do RWX. And this is easily satisfied by the fact that Alice is the owner of the file, so she gets RWX. Okay, now let's look at a more complicated example. So this is Bob. Bob is a member of engineering. Bob is not the owner of the file, and Bob wants R-X. So what happens here is that Bob doesn't match the owner of the file, so you go to the group. So the interesting point here is that Bob actually is denied access to the file to do r-x. The reason for that is because Bob is a member of engineering. Now, if Bob were not a member of engineering, Bob would have gotten the access to do r-x because of the fact that other users are allowed to do r-x. So this is what I mean when I say first match, right? So if Bob were not part of, because Bob is part of the group engineering, Bob directly is matched with those permissions. Now, why is this important? This is important when we compare with NTFS ACLs and when we try to understand how this applies to, how this relates to POSIX ACLs. So, I mean, this particular file permission, I try to replicate it in NTFS a little later. Okay, now we look at NTFS ACLs, right? So it basically consists of a set of ACEs. Order matters. There's no predefined order per se, but the order is specified by the ACL creator. So we'll look at some examples later. Here, the type tells us whether the permission bits are in the access mask are allowed or denied. The trustee tells us who the ACE applies to. Access marks are basically the permissions which are allowed or denied. The flags here actually tells us whether these permissions, how these permissions are going to get inherited. Like, for example, if this ACL is on a directory and you create another file or directory under it, it determines whether those permissions are inherited. But I'm not going to talk about inheritance in this presentation. Okay, so this is the access checking algorithm for NTFS. It's slightly more complicated than mode bits, but the thing to note here is that the second part of this slide is actually the ACL loop. And we only look at matched ACEs when doing this. And how is an ACE matched against a CRED? So that's the first part of the slide. So there are two ways in which an ACE can match a CRED. The first is if the CRED's user SID matches the ACE's SID, or the second is if the ACE's SID is a group SID and the CRED user is a member of the group, basically either by user match or group match. So if I were to summarize this access checking algorithm, right, so the gist of it is this. So you have an allowed mask variable here, and the allowed mask variable accumulates all the bits, all the allow bits which match that particular CRED. And let's say it's a deny ACE, and the deny ACE denies a requested permission which is not yet allowed. Then the permission is immediately denied. The first part, okay, so sorry, the thing I missed here is that if the allowed mask at any point satisfies all the requested permissions, it's an immediate allow. If the deny mask denies something which has not yet been allowed, then it's an immediate deny. So that's the summary of it. Any questions about this? Okay. So another point to note here is that we may or may not look at all the ACEs in the ACL. We may look at like the first few and we may decide it's allowed or denied, depending on what's allowed and what's denied. So here's the same example, right? So what we talked about a little earlier. So Alice, so the point here is that this set of ACEs is kind of supposed to match whatever mode bits that we saw a little earlier. You have Alice with read, write, execute, engineering with read, write, and everyone with read, execute. So this is the first example which we saw in mode bits. So if you are, I mean, when I first looked at this kind of stuff, right, I was a little naive and I thought that this actually matched the mode bits which we saw earlier. But it doesn't. That's the point of this. For the Alice, it does. Here, the allowed mask set is here. So if you look at it, the algorithm first looks at allow Alice read, write, execute, and it's granted. So, right? So in the case of Alice, the mode bits match the ACL. Everything is good. Now let's look at the second case that we looked at, right? Where in the previous example, Bob was member of engineering. He wanted read, execute. And here, what happens when you have the same set of permissions? I mean, cursory look at it will say that this is the same set of permissions. What happens here? So it looks at the ACL checking algorithm looks at the first case. Alice is not the owner of the file, so it's skipped. Now, Bob is a member of engineering, so he gets read, write. Now, the point here is you go further down, and the ACL checking algorithm actually looks at the next ACE, because nothing is denied at this point. So because of this ACL, Bob gets read, write, and execute. So although the bits look very similar to the mode bits, he's getting more bits than the mode bits. So how can you make this match the mode bits that we saw earlier. So one way to do that is to add a deny for engineering here, right? So then what happens is Bob is asking for read execute. You look at the first ace, it doesn't match. So you look at the second ace, it matches. He gets read, right? Then you look at the third ace. Now, execute here hasn't been allowed yet, and it's being denied explicitly. So his permission here is denied. So it matches the behavior, right? Now let's talk about POSIX ACLs. I mean, it is sad that there's so much of stuff here. This is the last presentation, but it is what it is. Okay. So yeah, so the POSIX ACLs are defined in the POSIX.1e spec. It is an extension of mode bits. Each file has an owner and group just like mode bits, and it's designed to work with mode bits. So what that means is that if you look at NTFS ACLs have no way, there's no spec which defines the interoperability with mode bits. But in this case, the POSIX ACL spec, which is part of the POSIX standard, explains, there is a good definition of what's supposed to happen when you do mode bit operations like chmod on POSIX ACLs. So we'll look at that a little later, an example of that. So here's what a POSIX ACL looks like, right? So you have type, name, and perm. This is the syntax, if you will, of a POSIX ACL, right? So the first part of the ACL is the type. It can be either user, group, or other. It can also be mask, right? But we'll talk about mask later. Let's just focus on user, group, and other right now. So if the type is a user, that means that this ace applies to a user, right? And if it's a group, it means it's a group. And if it's other, it means it other users in the system. So the POSIX ACL actually has 3 mandatory aces, one for the owner, one for the group, and one for other. So this corresponds to the mode bits, user group, other permissions that we saw earlier. So apart from that, you can also have named users and explicit named users and named groups. The second part of the ACL here is actually the name. So as you can see in the mandatory aces, it is actually null. The reason why it is null is because when the name is implicit, like if you're talking about the file owner, you don't need to specify the name. So if there is an ace which has a user ace which has the name as null, that means that it's for the file owner. Similarly for the file group, and obviously for other also there's no name. The permissions in POSIX ACLs are basically the same what you get for POSIX mode bits. It's RWX, read, write, execute. So here are 2 examples of aces for an arbitrary user Bob and arbitrary group engineering. Any questions? Not yet, okay, good. Okay, so here are this is an interesting point about POSIX ACLs. POSIX ACLs are evaluated in a specified order. So it doesn't matter what order you enter the aces in, but they always appear in a particular order. And they're always processed in a particular order, as in access checking happens in this order. So we'll look at the algorithm shortly in the next slide, but the point to note here is that the algorithm assumes that the aces are ordered in this way. Okay, so here's a POSIX ACL checking algorithm. And the thing to note here is that the first part of this is the part where you go through the ace list. And the second part is after the ace list. So this is the first part is the ace loop, basically. So there are 2 things to note here. This is actually a summary of the access checking algorithm. There's 2 things to note here. The first thing is that if you look at the first part of it, of the loop, this is how you do access checking for user aces. So if I were to summarize this, what we do is we go through the aces in a predefined order, which we talked about earlier. The ace match happens, like we talked about earlier, either by user match or group match. If it's a user match, all the requested bits have to be satisfied by that ace. So if we find a user match and all the bits are not satisfied by that ace, it's a deny. If it is satisfied, then it's an allow. So you're doing first match there for user aces. In group match, we do things slightly differently. If there is a match with a group ace, we see if that group ACE satisfies all the requested bits. If it does, then we allow the user to do whatever operation he wants to do. If it doesn't, we don't do a deny at that point. What we do is we look at the next group ACE. We actually go through all the group ACEs, and we look for a group ACE which satisfies all the requested permissions. The gist of this, or the crux of this, is that we don't do bit accumulation, right? Like NTFS ACLs. We don't collect all the bits of matched ACEs. We only allow a group ACE. We only accept a group ACE if it gives you all the bits that you requested for. The second bullet here is actually the other ACE matching thing, which we looked at in mode bits. So if no group or no user is matched, then only in that case do you look at other ACEs. And if the other ACE gives you the access to do what you want to do, then permission is granted.
Question.
Yeah.
What if the user is a member of a group that's a member of the group that's being matched?
A user is a member.
Is a member of QA that's a member of the nested group. So he's a QA, but he's a member of engineering, and we're checking for group access.
So I believe you, so let's say there is QA and, what is the second one?
Yes, so QA is a member of engineering group, and we do
So I think it just checks whether, so your CRED has all the groups that you're a member of, and you see whether any of those groups appear here. So it doesn't matter even if it's nested. You actually enumerate the whole list in the CRED. I think the question was, what if you had nested group memberships? What happens? So the answer is that all the groups that you're a member of are enumerated in the CRED. So there's no nesting in the CRED per se. So as long as the CRED in the group in the CRED matches whatever's in the ACE, it's a match. Good question. Okay, so here's the same Alice and Bob example, and here we're looking at Bob, right? So Bob here, in this example, has an explicit ACE, right? The second ACE here is specifically for Bob, and it grants read, write, execute. So the way it works here is you look at the first ACE. Bob is not the owner of the file, so you skip it. You look at the next one, and Bob, there's an explicit ACE, and it grants read, write, execute. So done. Now, here's the third example. So here the user Clark, for the user Clark, there's an explicit ACE for which grants just read. And Clark wants read, write, and Clark is also a member of engineering. And if you look here, engineering actually has read, write permissions. But this is the way the algorithm proceeds. The first, it checks whether Clark is a member of the file, is the file owner, he's not. So you move further, Clark is not, Bob, you look at this. So here, this ACE grants Clark read permissions, right? So you're granted read. The point here is that the algorithm doesn't proceed further after this point. What it does is, because Clark is asking for read, write, and this ACE explicitly only grants read, we follow first match semantics, and it becomes a deny at this point. Okay, now let's look at the multi-group case. So in this case, David is a member of engineering and sales. So sales grants read, and engineering grants read, write, and he's requesting for read, write permissions. So what happens in this case is, again, David is not an owner of the file, so this is skipped. You go to Bob. Again, it's a user ID mismatch. You get to Clark, mismatch, and you get to sales. Now, this is the interesting part. So here, he's requesting for read, write, but the group ACE only grants you read. But because it's a group match, the algorithm, what it does is, it checks whether this ACE grants both read and write. It doesn't, so it moves to the next ACE. And here, it gets both the bits, so access allowed. Okay, so David is granted read, write because we check every group and try to find the one that grants all the bits. So that's the difference in behavior. Okay, so now moving on to mask case. So mask case is this new ACE type, or new kind of ACE type, which was defined in POSIX ACLs. So if I were to summarize what mask case is mask case is something that the bits in the mask case are define the upper bound of the permissions for every group in the ACL and every named user, okay? So we'll look at an example of this a little later. So it is primarily used to support chmod. So if you look at this chmod example, you're doing chmod 654 of the file. And the way the POSIX spec for ACLs defines this is that the user ACE gets the 6 here, the 5 goes to the mask case, and the other goes to, the 4 goes to the other. So if you think about it, it's kind of a definition of how chmod should work with these ACLs, right? Which is missing in NTFS, in the NTFS world. So if I were to summarize what the mask case is, the way the group mode bits in the chmod is, right, according to the POSIX spec. The POSIX spec is basically telling us that the group bits of the chmod apply to every named user and every group in the ACL. That's what it's essentially saying. So the group has been, the notion of group has been expanded to include every named user and every group. So here's an example of what I'm talking about, right? So here is the same ACL which we saw earlier where the user David is actually a member of sales and engineering. And earlier he had access to read and write the file. But in this case, there's a mask case which restricts the permissions to read. So what happens as a result is that David only gets read now. Because the mask, again, what I mentioned earlier, is the upper bound of the permissions that can be granted to every named user. In this case, Bob and Clark and sales and engineering are all included in this, will only get read, no matter what permission they have in the ACL, right? Another thing to note here is that the file owner and other are not impacted by the mask case in any way. It only applies to all named users and every group, including the file group. Questions? Okay. Okay, so I think I've laid the groundwork, at least as much as I could within the permitted time, to get to the implementation, right? So we had requirements to implement HDFS ACLs in OneFS, and it was very high priority requirement. We had to meet it. So like I said earlier, we support Modbits and NTFS ACLs in OneFS, and we needed a way to support HDFS ACLs. And as you can imagine, the POSIX ACLs are a completely different beast as compared to Modbits and NTFS ACLs. So how do you support this, right? So these are the approaches that we considered. So one approach was to translate the POSIX ACLs into OneFS or the NTFS style ACL and write that to disk. So essentially what you're doing is you are making the NTFS permission checking algorithm provide you with the access checking semantics of a POSIX ACL. Right? That's what you're trying to do. And the second option is to just support POSIX ACLs on disk. So what this means is that you need complete support of POSIX ACLs everywhere in the file system. You need a new access checking algorithm. And any point in the kernel where you actually go and test or touch a ACL, you need to take care of this structure. The thing to note here is that bullet 1 is actually a subset of bullet 2. Because the translation algorithm which you need to go from NTFS to POSIX and POSIX to NTFS, you have to implement it anyway if you want to support HDFS ACLs in any form. The reason for that is that we are a multi-protocol file system. And if you want to support SMB or NFSv4, an NFSv4 client or an SMB client might actually open and try to read a file which is written by HDFS. So then you have an HDFS ACL, and you want to read it and make sense of it as an NTFS ACL. So you need to do translation anyway, right? So these are the trade-offs, right? So if you were to do pure translation, the complexity is low, there's less code, most of the code or all of the code lives in user space. But the disadvantage is that there's no mask case. There's nothing analogous to a mask case in the kernel for NTFS. So there's no way for us to support a mask case. So as a result, there are a lot of inaccuracies. And even if you had support for a mask case, there are still going to be inaccuracies because of the fact that NTFS ACLs and POSIX ACLs are completely different things, right? So now these are trade-offs of putting it directly on disk. You get very high accuracy access control because you now have ACL directly on disk. You can actually do proper POSIX ACL chmod because you have the mask case on disk. The major disadvantage with this is that there are extensive changes that are required in the file system, right? And there are extensive changes that are required in the file system, and it's not clear whether those changes will translate into something. It's not sure. We are not sure how many customers are actually going to use this product, and making so many extensive changes in the file system for maybe a small subset of the customers is probably not warranted. So this is one of those situations where there is no absolutely correct solution. There are going to be trade-offs, and you need to decide what your trade-offs are, right? So what we went with the middle path. What we did is we translate from NTFS ACLs, translate to NTFS ACLs on disk. So we take the POSIX ACL from HDFS, we write it as NTFS ACLs. But then because this is OneFS ACLs and it's a superset of NTFS ACLs, we added a new ACE type called mask ACE. And that mask ACE actually implements the semantics of what you need from the POSIX mask ACE. As I mentioned earlier, there's nothing analogous to a mask ACE in NTFS, so you need something new. The other point to note here is that we changed the way the system calls work, such that if SMB were to read the ACL, we would go and do some tricks, I would say, to make sure that the mask ACE is not visible to SMB. And we can do it in a consistent way, which actually doesn't make the whole thing unpredictable. So I'll talk about that a little later. So the gist of this is that the HDFS ACLs are only visible to HDFS, including the mask ACE. So if you look at the trade-offs of this approach, right, the complexity is definitely low. Most of the code is in user space. There is, I grant you, there is actually some amount of code in the access checking algorithm in the kernel to account for the mask ACE, but apart from that, almost all of the code is in user space. The access control for this is more accurate than what you would get by doing pure translation, because now you have the mask ACE in the kernel. The disadvantage is that it is definitely a lower level of access control, a lower level of accuracy in the access control as compared to putting the POSIX ACL directly on disk. I mean, there's no way around it. That is a fact. Another advantage of this is that this is a good first implementation. What that means is that you can, like I said in like 2 or 3 slides earlier, the point here is that if you're doing translation is essentially a subset of the full on-disk implementation. You need to do a translation algorithm anyway. So this is sort of like a halfway implementation. Now, if we deploy this and customers come back saying that there's this small access checking thing which is creating a problem for us and it's really bad, you should implement the full thing, then we'll go and revisit this, right? So we kind of wrangled with this back and forth for a long time, and finally we went with this. So we haven't heard anything from the customer yet, so we're hoping that this will be good enough. Questions? Yeah.
What do you just translate the mask to something not used? For example, if the mask only read it, right? Then you can deny the right execute everything. Is that possible?
So I think the question is, can you? Yeah. Yeah, I'll try to repeat the question as I understood it. So I think the question was, is there some way to translate the mask case into something which is more generic to OneFS? So what you're asking for is to translate something, the mask case into some ACE in NTFS, which limits the access of every named user and every named group in the ACL. The answer to that is it's a mathematical problem. It's a set theory problem. And it's not clear to me whether you can solve that for every possible set and every possible ACL. It's a very hard problem. It's a mathematical problem. So I would say that it might be possible, but then it's sort of like one of those things where you solve it for one ACL, and a customer might have some weird convoluted ACL where your translation might be messed up. I mean, I'm not sure. Maybe there is a solution. It's a really hard problem.
So do you allow the access from a masking secure data set over multiprotocol, or just limited to HDFS?
So when an SMB client, okay, the question is, do you allow the mask case, a translated ACL to be accessed over multiprotocol, right? Yes, you do. So the way it works is that if you come over SMB and you try to access the file, the access checking algorithm kernel accounts for the mask case. So you get an access control which is consistent with what the mask case would provide you on the POSIX side. But if you were to read the ACL, what we will do is we would take the mask case, and what does the mask case do? The mask case is the upper bound of the permissions for every named user and every named groups, right? So what we will do is, let's say it is r dash dash, right? We will make sure that when we return this ACE to SMB, we'll make sure that every named user and every named group in the ACL doesn't have anything more than read. Does that make sense? Yeah. So that's what we do.
Do you allow the NTFS to mask ACE modification of ACE?
So that's a good question. The question is, do you allow the NTFS to write a POSIX translate?
We modify ACL, NTFS ACL, and get all the results.
We have to. The answer is we have to. The reason is that, but the point here is that, let's say an NTFS client were to read the ACL back into user space, into a Windows client. What would happen at that point is that now you have an NTFS ACL, right? A translated NTFS ACL. And let's say if it were to modify, it's not seeing the mask case at that point, but the mask case has already been removed. So now if you do a set of that permissions, right, by adding an entry or something, you have now written a pure NTFS ACL. So now it doesn't have mask case, it has lost information.
So does it discard mask case or it modifies it?
The way the NTFS permission, the write permission thing happens, it's a set. So it's an overwrite. So it's like I read 3 and I write 4. So now it's 4. There's nothing, the 3 is gone completely, right? So there's an example of this, I'll come to that. So now, I initially when I did this presentation in-house, I was actually explaining the whole translation algorithm and all that, and it's really, really, like, I would say mind-numbing, right? So I don't want to get into all that stuff. So what I would say is, it's loosely based on the draft IETF NFSv4 ACL mapping spec. So this is actually a collection of specs. I think there are like 4 or 5. Are you guys aware of this spec?
Is it draft file plan?
Yeah. Yeah. Okay. So it's like 3 or 4 specs, and I could talk about it ad nauseum, but I'm not going to go there. But this is what we do. So if I were to summarize this, what we essentially do is, we talked about the first match semantics and all that stuff, right? So what we really do here is for every POSIX entry, POSIX ACE entry, we translate that to an NTFS ACL, and then that is followed by another entry, which is a deny, right? And the deny is for the same trustee, and the deny has what I would call as inverse of the allow entries mask. So an example of this is, in this case, right? If the allow is RW dash, then the deny will have dash dash X. Why do I do that? Because I want to enforce first match semantics, as we saw earlier. You remember the Alice and Bob example, where Bob got read, write, execute when it went to NTFS, but in mode bits he only got read, execute, right? So to enforce those semantics, I do this. Yeah? I know, I agree. But the problem here is that I try to follow this idea, which comes from the NFS spec, where you say that you should not convey a message to a protocol client that your resource is more secure than it actually is. So now if you remove the deny ACE, right, you are actually telling the client that it is really secure, right? It is really secure.
Instead of putting deny ACE, you remove a corresponding allow ACE permission.
If you remove the allow ACE, then you won't get a read write at all in this case. Yeah, but again, to summarize, the stuff that I don't have in the slide is that we try to do this thing of not presenting security information to the client, giving them the feeling that the resource is more secure than it actually is, which is something we want to avoid. Now, adding a deny, as you said, it is unpredictable, but like I said, this is a problem which doesn't have any clean solution. Any solution that you take has some drawbacks, so we went with this. So here's an example of what that looks like, the translation, right? So it's very intuitive, and I'm not going into too much of the details. So for Alice, it's a read, write, execute. So here I assume that read, write, execute translates to R and RWX. In reality, on the NTFS side, a read corresponds to read attr, read data, blah, 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 all that stuff. So I kind of assume that, yeah. So for Bob, read write corresponds to deny Bob execute, and then group corresponds to read write, and deny corresponds to execute. And yeah, it's pretty intuitive at that point. And it has to be in this order. That is the point. So the OneFS ACL has to be in this order because this is the POSIX canonical order, as in the way the POSIX ACL actually is evaluated by the POSIX ACL checking algorithm. So it has to be in this order. For the mask case, we have this new A step, and we just say read. And within the file system, the access checking algorithm, we go and do what we need with the mask case. So just for completeness, one thing to note here is that the translation from POSIX to OneFS is order of n, the size of the ACL, and back also it is order of n, the size of the ACL. But backwards, I think it also requires order of n space. Yeah?
Isn't the design and pace has a high priority than
So the question is, does deny ACE have a higher priority than allow? So that is something that comes from what is known as the Windows canonical order. So basically what it means is that in the Windows world, right, if you try to add allow and deny ACEs, the application or some layer in between actually orders the ACEs such that deny show up above allows. But that doesn't mean that the order of evaluation always looks at allows. In the NTFS world, the order in which the ACLs are evaluated strictly follows the order in which it is specified, right? So when you say that denies have precedence for allows, that's because the applications on Windows actually order it that way. So there are some properties of this. I'm not going to geek out on this, but this is the point, right? So if an HDFS ACL, if HDFS writes an ACL and reads it back, it can expect to get whatever it wrote, right? The reason for this is a little subtle, but the point here is that if you think about it intuitively, the allow ACE of the ACL, as I think you pointed out, kind of corresponds to exactly to what was written in the POSIX ACL. So the allow ACE can be translated directly into the POSIX ACE without loss of information. So if an HDFS ACL writes ABC, it can expect to get ABC back. Whatever it wrote, it can get. That is true all the time. The second point here, which is very important, is that if you take any arbitrary NTFS ACE, right, like you said, you were saying that about the priority of deny and allow and all that, right? So if you look at an ACE which is an arbitrary NTFS ACE, which has a lot of denies followed by a lot of allows, the algorithm actually tries its best to get a very good representation of that in the POSIX ACL world. But the problem with that is that the NTFS ACL space is very huge compared to what can be represented in POSIX, right? So there are going to be inaccuracies. There's no real way for you to, or let's say there's no known way for you to get a good representation on the POSIX side. Now here's where it gets really into the weeds, right? So there is one case where there is still an inaccuracy, even after doing all this. But if you were to take a POSIX ACL and convert it into NTFS, there is one specific case where things can go wrong, right? So that is the case where you have multiple groups, and if these groups cannot be ordered such that the bits cannot be ordered in non-decreasing order of mode bits, then you can potentially have problems. The reason for that is, again, subtle. I have an example for it at the end of the slide. If there is time, we can get to it. But it may not be of interest to others. But there is one specific case where it can be a problem. We'll see if we have time. We'll look at it. I put the example at the end of the slide. Any questions? Okay. So related issues, right? So these are things which showed up later during the development, right? So one thing to note here about the HDFS design. So HDFS is, I think most people here know about it, but I'll just summarize. So HDFS comes out from the Google white paper where you have a single name node or single metadata node which contains all the metadata in the system, and it basically expects all the metadata operations to be in single-threaded. And there are multiple data nodes, and the HDFS spec basically defines data files to be like in multiple, very large files, gigabits of size. And the basic idea here is that you have high data throughput and very low number of metadata operations. And they use prefix compression for paths and stuff like that to cram in as much of metadata into a single server. On the OneFS side, HDFS is like any other protocol. OneFS is a generic scale-out cluster. Every node is identical. Every node has data and metadata. So because of this difference in the way things are designed, there are problems which arise. So the fundamental problem is that some of the HDFS operations, as they are defined in the protocol server, right, they involve read, update, write cycles. So what I mean by that is, let's say you have an ACL, and okay, let's take this example. If you look at chmod or modify, there are certain operations where the on-the-wire protocol op will send you an ACE, and you are expected to read the ACL from disk, consolidate the ACL with what was sent to you, and then write it back. So the problem with this kind of an operation is that the protocol server now has to read the ACL, update the ACL, and write it back. What makes this even more complicated is that the way the HDFS protocol works is that it assumes that large reads and large writes can happen in parallel with these metadata operations. So on the OneFS side, what we really need is a way to lock down the metadata of the file without blocking any of the reads and writes, which is something that in user land, if you think about it, on any operating system, it's not there. You don't have that kind of a locking, where you just lock the metadata and allow. So what we do have is what is known as shared locks, which allow you to lock down the whole file or lock specific byte ranges. So we didn't have a lock which would do this for us. So the way we solve this problem is this, right? So when we write the ACL to disk, when we do the read, update, write on the protocol server, when we first read the ACL, the system call, I modified the system call to basically return a hash, and or a generation number or whatever you call it for all the permissions on the file. So now when you write back the ACL, you send back this hash. So now if there are two concurrent writes of the permissions on disk, the second one will basically have a stale version of the hash. So which means that two operations raised and the second one lost and the first one won, right? So that's what we do. So ACL write passes in the hash. If it doesn't match, we return a retriable error, and that's what we do. The alternative to this was to have a special metadata distributed lock within the kernel, which seemed like a lot of work. Distributed lock which could be handed out to user land, which seemed like a lot of work. So now the thing here is that if you think about it, right? So this is a form of optimistic concurrency control. This is something that comes from distributed DB literature, right? Where you can have multiple concurrent transactions, and you allow the transactions to execute to completion and without locking. And once the last operation commits, you see whether there was a conflict. If so, then you roll back the second one. So this is from the database literature. And this optimistic concurrency control is known to work really well when the contention is really low. The opposite of optimistic concurrency control is pessimistic concurrency control, where you lock down the whole file and you do your operation. So in the database world, that means that you lock down all the records that you want to modify, and then you do your operation. The problem with that is if the contention is really low, it becomes very expensive. So this, I would argue, is a very good solution for this particular problem, because it's very rare for you to have multiple metadata operations conflict in HDFS. I have one more slide, and then we can get to questions. So the last problem here was related to replication, right? We in OneFS support intercluster replication, and we support replication from version X to version X-1. So the problem there is that the version X-1 doesn't have the mask case, right? So if you were to replicate OneFS ACL to a previous version, you literally end up with a file which is less secure than what you started with. So how do you solve this problem? There has to be a way for you to, or we would like to have a way to do replication such that the security is maintained. So the way we do this is, we do this, right? This is exactly the same operation that we do for when an SMB client tries to read a POSIX ACL. So on the left is the ACL which has the POSIX mask. It has R dash dash. All the letters here on the left which are in red are the ones which are denied by the mask. So what we do is we, in the thing that we replicate, in the ACL that we replicate, we just remove all those bits. And now we have an ACL which is at least as secure as the one before replication. And that's it. I actually have the other slide for the translation inaccuracy. We can get to it. Oh, sorry. Yeah, but yeah, any questions? Yeah.
Apples are always a problem.
Yep.
So, how
Yep.
many issues have you found deploying your solution?
Nothing yet. Good question. So we have had lots and lots of ACL issues in the past, right? So there is, what I've seen in the past is that nobody's happy with security, right? And I expect there to be issues here, but we'll face them as they come. I mean, that's what I can say. Yeah. So so far, I think the customers who have deployed this haven't come back with this particular inaccuracy problem, but I have seen a bunch of other issues related to multi-protocol where people come back saying that like recently, I mean, people, I don't want to get into specifics, but they will come back saying that, you know, we want to do chmod on this particular ACL, and we have this migration task which is doing all this stuff, and your chmod is not the correct implementation, right? I mean, right. So, and they will say that this is the way chmod should work, right? And then overnight you need to implement your own version, their version of chmod, and you need to provide them a config knob, and they're happy, right? Yeah, I mean, this has happened. I mean, it happened like last year. So, I think there was another presentation where somebody said that if you throw enough money at it, then any problem can go away. So, yeah, people are ready to throw money. So, sort of. Yeah.
There's a question about the POSIX ACLs.
Yeah.
Is this a commonly requested by customers feature? And why would they use it versus, for HDFS? Obviously, we're talking about HDFS.
Yes, so it is. So the question is it, do we get these requests from customer for doing POSIX ACLs? So Apache HDFS actually implements POSIX ACLs, and there are multiple use cases involving Hive. I don't know the specifics of it, where customers really want this. So this, out of 1,000 requirements which we had, this was the topmost priority for last year. So.
It's driven by Hive requirements for.
Yes, but I don't know the specifics, what they're using it for. And I think, yeah, I know some of it. What they were saying is that they are using mode bits from on the HDFS, I forgot the name of the tool. Ambari? Yeah, Ambari, I think. Yeah, on Ambari they wanted to set permissions on the file, which were not just for user, group, and other. They wanted to provide permissions for specific users and groups, and that is something that was sorely missing in the product, and they really were unhappy about it.
The Ambari is a management framework, right? So that
Yes.
will be more granular.
No, I think they were using Ambari to set up the permissions for Hive. I think. I mean, this is based on, so I don't work on HDFS. I just work on the file system and the security part of it. So this is what I heard. So, yeah. Do you guys work on HDFS?
We worked with before.
Oh, worked before. Okay. Okay. Yeah. So this is one of those things where we really, the customers really wanted it, and we couldn't come up with a solution which would make everyone happy. I mean, if you had gone up with the full file system implementation, a lot of people in the file system opposed it because it's a lot of changes, right? So we are hoping this will work for all customers. If not, then we'll see. So I guess that's it. If there are no more questions, so I'll be around, so you guys can reach out to me.